Well, a very good morning, dear, and welcome back to the lecture of Mathematical Foundation of Robotics. Today, we are going to learn a very interesting, very important topic known as Dinavate-Hartenberg notation, and also you can call it Dinavate-Hartenberg principle, and that is widely used for modeling a robot in a form which will be understandable by the computer. Okay. First of all, let us try to understand why at all we have a coordinate transformation, homogeneous coordinate transformation matrix we have, and we have also transformation operation. You see, just by anywhere in this open kinematic chain, okay, anywhere if you have a point, okay, and you know its position vector with respect to inertial coordinate frame, or as such with respect to any coordinate frame, okay, what will be its description when the link is moving, I can capture using 4x4 homogeneous coordinate transformation matrix. Then why do we need DH notations, Dinavate-Hartenberg notations? The reason is, you see, the homogeneous coordinate transformation matrix does not carry the physical informations of a generalized link. Say this link, intermediate link, is twisted. That means one end with respect to the other end, and it may happen, right? In a generalized way, I can construct a robot where any link with respect to in a link between two axes of rotation, there could be a twist. And also, if what if I bend the link also? So we should have a generalized way. Even it is bended, how can I get the link length? Okay, and even if it is twisted, how can I accommodate that information in my homogeneous coordinate transformation matrix? And precisely, you see, there could be, say this is one axis of rotation, this is our very well known Puma robot, the grammar of robotics, okay, learning. So this is one axis, and another axis, this is elbow, right? Elbow and shoulder, they could be, the axis of rotation could have a projected distance between them. So how to capture all this information and formulate again a modified homogeneous coordinate transformation matrix is the purpose of studying Dinavate-Hartenberg notation. This is, you see, 1955. It's very old, right? But it's a classic paper. J. Dinavate and R. S. Hartenberg actually described how in a kinematic chain, how between any two successive link, kinematic relationship can be established when one is moving with respect to the other. Okay, let us consider here. So this beautiful picture, okay, and this is all revolute joint robot. Okay, that means all the axes. First of all, whenever what we are trying to do, we are trying to establish kinematic relation in the form of a matrix between two successive link. Okay, so here I have two link. This is one link, and this purple color is another link, and this two link is connected by a joint, and one end is actually again ready to connect another link, and this is also ready to connect another link, like that. Okay, so this could be accommodating another link. Okay, this could be also accommodating another link. So this is an intermediate link. Okay, and wherever you see the axis of rotation, the rule is you assign z axis towards that. So you see, this is my this is you see axis I, which is assigned to the link I. Okay, and you see every link at the left hand side I am attaching coordinate frame. This rule need not be followed always, but there are two books, John J. Craig, which is your textbook, and in my library I have sufficient copy, maybe 100 copies, so that all of you can have one copy. So there the convention has been followed that this is a rigid body, okay, and at the left hand the coordinate frame, body coordinate frame, will be attached to describe this link. Okay, here also you see this is link I minus 1. So where will be its axis of rotation? Z axis. Z axis will be at the left where it begins. Okay, and in some other book also it may happen that you at the end of that link you can put that axis, because it is a body coordinate frame. It hardly matters. You can put it here, here, here to describe any point on the body, but you will have to be judicious. Okay, I should attach coordinate frame where it is convenient for me and it makes some logical sense, which you will see. The minimum number of parameter I will try to attain with some manipulation. As we proceed further, you will know. So wherever you can say how many this is two, so this is link I minus 1. There are 3 joints, okay, and Z axis will be assigned here. So Z I plus 1, this is Z I, and this is Z I minus 1, okay. And you see this link, as I told you, has a twist, okay, and the twist is in this purple color link I is twisted in the direction of rotation of the in a clockwise direction. Okay, in a clockwise direction, this end is twisted with respect to this end. Okay, so so there will be a twist angle. So what is the twist angle? It is the angle between two successive Z axis. Okay, so if this is also twisted with respect to that, so that is the angle between two successive Z axis. Okay, so this Z I minus 1. Okay, so and how it will be measured? And now let us try to understand that how we can attach coordinate frame. The convention is wherever rotation axis is there, you assign Z, and you see the direction of the common normal. So you see the link could be of any shape, okay, but what is the common normal which is characterizing the link length? Why it is characterizing link length? Because with respect to common normal, okay, if this is the coordinate frame, any body's ith link's position vector will be completely, as long as it's a rigid body, will be completely unchanged. Okay, so coordinate frame only if we figure out the relation, then only multiplication will be with a known vector, right, to get its position. Just earlier we discussed it also. I think it is clear, right? So this axis actually is describing the link length. Okay, about this axis the link length is measured. What is link length? It is the distance between two successive axis, two successive rotation axis. Here it is rotation, here it could be translation. Okay, it's a combination of rotation and translation. Prismatic joint is here. So this is revolute joint, and here you can see this is a prismatic joint. So why Z minus 1? Where Z minus 1 has to be assigned? Wherever you can see the motion, the prismatic joint, right? So motion of this link will be in this direction, and this can accommodate somebody which has a revolute joint kind of thing. Okay. Okay, so this is the two figure shows you revolute type of robot RRR type of robot, okay, and this is RPR type of robot, okay. So here it could be another revolute joint, this prismatic joint. One prismatic joint is necessary to show you. You will understand why, okay. So that there will be clearly clear notion in within you that how DH parameter works. So far so good. So wherever you have rotation axis, motion axis, not rotation, motion axis, you assign Z, okay. Just like link I, ZI should be here at the left. This is the convention of our notation. So ZI, and where will be X? X will be, you figure out what is the distance between two axis of rotation, okay, and that characterize the link length, okay. So what will be the so this is perpendicular, this is perpendicular, this is spatial structure, so you need to understand. So this and this is the common normal. This is the common normal. Why it is common normal? Because this is normal to the ZI axis, this is also normal to the ZI minus 1 axis. Similarly, you see this is ZI axis and this is ZI minus 1 axis. And then what will be the common normal? Common normal will be, so this is a common normal, okay, AI minus 1, and it is measured along XI minus 1, okay. So X axis will be directed towards the normal, and that along that axis the link length will be measured, okay. And where motion will be along this axis, so this will be theta I plus 1, along this motion will be theta I, this theta I minus 1, like that. So AI is the common normal between ZI plus 1 and ZI. Similarly, AI minus 1 is the common normal between this ZI and ZI minus 1. Now you see, we do not want, this is not necessary actually, because we are talking about orthogonal coordinate frame. The moment X and Z are fixed, so this cannot have any other direction. Whether you show it in the figure or don't show it, it is understood that YI will be in this direction, because right-handed Cartesian coordinate frame we are using, okay. To avoid clumsiness, sometimes we will avoid the other three axes. It's not needed, okay. It is understood. So you see, here is the origin of the ith coordinate frame, okay, and here is the origin of the I minus 1 coordinate frame. So this is a common normal, this is another common normal, and the distance between these two common normal, is known as di, and it is measured in the direction of z, okay. So distance between two successive common normal is denoted as di, and the length of the axis, which is actually common normal, is denoted by AI, okay. And you see the rotation parameter, motion parameter is either could be theta or it could be di. You see here, in case of D will be varying here in case of prismatic joint. In case of revolute joint, variable will be theta, okay, because link will be moving like this, okay. And then one more parameter, so three parameters already you know, and one more parameter which is required for generalized modeling of two successive link. What is that? You see, the twist angle, how the twist angle is measured. You know, you can project ZI and Z I minus 1 on YZ plane. So here Y may be useful for your understanding, okay. Okay. this is actually okay in this. Okay, so YZ plane, you just put your Z I axis, okay, Z I axis, and this is Z I minus 1, okay. So you see this is projected Z I, so this and this are parallel, that's why. And the twist angle is the angle between this projected J I and Z I minus 1. And how it is measured? It is measured about x axis, x I minus 1 in this case. If the twist angle is here, with this end is twisted with respect to this, then there will be measured about xi, like that, okay. So about xi minus 1, the twist angle is measured, okay, and along Zi, the distance between two successive common normal is measured, and along x-axis, that respective link's length, which is common normal, is measured, and the motion parameter is measured about z-axis. It could be revolute, theta could be revolute type of joint in degree, and di could be in distance, centimeter or feet, length distance, right, if it is prismatic joint. So having understood that DH notations, so there are 4 notations, okay, theta, then A, then D, then alpha, okay. These are the 4 parameters. Alpha denoting the twist angle, that A characterizing link length, theta characterizing the rotation parameter, okay, and di characterizing the distance between two successive common normal. Clear? Okay. Now come to the next point. Say now we have identified only, now we need to deduce the very simple relation, okay, so that our matrix again will be 4 by 4 and will carry all these generalized parameters inside it, okay. So you see this is axis I, this is link I minus 1, this is link I, okay, it is extended again, you see here it could be carrying, okay, another and this can continue as a chain, okay. This is I plus 1 axis, so on and so forth, okay. So we have identified 2 axes, x Zi, Zi minus 1, and you see now this is the coordinate frame characterizing the link I. So this is xi, which is directed in the common normal, okay. The common normal could be the minimum distance between two successive is a common normal, right? So this will be ai, like that. So you see this is the x-axis, which is assigned for describing the common normal. This is the z-axis, okay, and say this is p coordinate frame, okay. Now it could rotate in this direction, clockwise is anti-clockwise positive, clockwise is negative, like that we can so let us assume that initial coordinate frame was like this, and then I have this is ith coordinate frame, and I minus 1 coordinate frame is here. Again xi will be in the direction of common normal, okay. So this is xi minus 1, and zi minus 1 will be in the direction of rotation. Now you see what is our objective. So ith frame will be completely superimposed on I minus 1 prime, so that we can, and whatever transformation is required, we will do that. Okay. Sometimes we note by this, sometimes we denote by this. That means the position and orientation of coordinate frame I with respect to I minus 1. We need to figure out this. How? Just, you see, by superimposing, and in that process whatever transformation will be required, we will do that. So what we will have to do first, you see, bring this by this origin, translate in the direction of z by an amount di. So now it comes here, and then say earlier it was theta I rotation, now you give another operation so that it will be perfectly aligned here. So bring down along z this, then rotate it about z theta angle, so that now P will be like this. Okay, and then take the origin, translate it along the a I minus 1 axis here. So so PQ, this PQ, and this is we are calling R to just tell you the full story. So you are snatching it like this. Now the angle between these two z axis is called twist angle. So completely superimposing this with the, I need to rotate about this by an amount alpha I minus 1, so that this and this will be completely overlapping. And as a result of that, so as a result of these operations, which we told, there is 4 operations, right? So one translation, another rotation, another translation, another rotation. So these are the 4 transformations which are required to completely superimpose ith coordinate frame with respect to I minus 1 coordinate frame. Okay. Now you see, this is the story which is being captured here. So this is one operation, this is another operation. So these operations are actually 4 operations have been beautifully written over here. I hope you understand. Okay. So one translation and D, then rotation about Z, then about X, alpha I minus 1 is a twist angle. This is a common normal, okay, ai minus 1, and this is twist angle alpha I minus 1 about x. Okay, so if you give this 4 transformation, then I and I minus 1 will be superimposed. That means that is the relation which we need to figure out. Now, my student, up to this is fine, you understand. Always my student can come up with a different kind of matrix, but there should not be any confusion. You can see refer my earlier video lecture where I have told that how the rotation matrix, because the matrix are order dependent. In transformation matrix, homogeneous coordinate transformation matrix has a rotation matrix inside. So they are order dependent. So how to figure out this? First, make I, which is 4 cross 4 identity matrix. Okay, and then consider, because I am figuring out ith coordinate frame position and orientation with respect to I minus 1, So I minus 1, let us consider it as an inertial coordinate frame, and I coordinate frame is a body coordinate frame. Okay. Now, as you know, whenever you give operation, you give transformation about or along, in this case about any of the body coordinate frame, then matrices will be post multiplied. Okay, so what about 3 and 4? 3 and 4 will be post multiplied. And what will be 2 and 1? Because 2 and 1 is, see, operations are giving along x-axis, about x-axis, along x-axis, about x-axis, right? So this I minus 1 actually is acting as an inertial coordinate frame. Okay, in case of two successive, two link. Okay, it can also move, but for this particular derivation, we are assuming that I minus 1 is inertial coordinate frame. So there will be no mistake if you follow this. For example, you can argue that first, instead of doing 4 should be 3. first I will give rotation about z axis. Okay, instead of translating first d and then give rotation, I will first give rotation about z axis. Okay, that is possible. Okay, do it. So you give first rotation about z axis by an amount theta I. Okay, then followed by translation. Okay, and by an amount di. Okay, and then followed by dx alpha I minus 1 followed by dx ai minus 1. This is perfectly possible. If you do, you will get the same resultant matrix. Means this can come here, this can go there, this can come here, this can go there, but the operations whenever you are giving with respect to here with respect to ith coordinate frame, they will be post multiplied, and with respect to I minus 1 coordinate frame, they will be pre multiplied. This we have proved. Why? Because inside T there is a there is a rotation matrix, and this is an orthogonal matrix. So you see, we have even deduced that why it should be like that. Okay, it's a good exercise, or you can refer to my earlier lectures. So that all I wanted to tell you, and then you see, very good. Now you understood. So what is this matrix? This is very very nice. So this 4 cross 4 matrix, rotation about x by an amount alpha I minus 1. So 1 0 0 0. This is 0 0. This is about x, right? So you know already. This is the submatrix, which is rotation matrix. Okay, and you already know my earlier lecture. Okay, so this is very simple. And then since this is only rotation, so here all will be elements will be 0. So this is what it is. Then why? What this one? So 1 0 0 ai minus 1, because you have translated about x by an amount ai minus 1. Okay, so here this is x along x, and all other will be this is a unitary matrix because no rotation is being given here. Okay, so we are keeping as it is our unitary matrix, and all other elements are 0. Okay, so this is this one. Now this guy, you see, you have rotated about z by an amount theta I, so cos theta, and this is the rotation submatrix. Okay, very easy. Earlier you know, and all other are 0, and this is 1 4 cross 4, and this is along d. This is the simplest matrix, right? Along z axis by an amount d, so x y z amount d. So this is this matrix 1 2 3 4. So 4 matrix has to be multiplied. Okay, so what I just told you, that it will never change if you first do this. So if it is coming over here and then it is going over there, it is coming over here, it is going over there. So it's a good exercise, but do not mix. Means you cannot put it here. Why? Because I have told you this is there is a I 4 cross 4 matrix. If you just do this, you will never make any mistake. Okay? And so this is the matrix after multiplying these two, and this is the matrix after multiplying these two. So let us quickly go through. Okay. So we have two matrices. So what will be the resultant matrix? Now we will have to multiply these two matrices. 1 0 0 a I minus 1. Don't worry, I am just rewriting the cos alpha I minus 1 minus sine alpha I minus 1 0. Okay, 0 sine alpha I minus 1 cos alpha I minus 1 0 0 0 0 1. So this is one matrix, and this is another one, cos theta 1 minus sine theta I actually generalized representation cos theta I 0 0, then 0 0 1 di. Okay, so if you multiply these two, you will get this very, very important matrix. Sin theta I, then 0, then I minus 1, second row is sin theta 1, okay, cos alpha I minus 1, cos theta I, cos alpha I minus 1, then this is minus sin alpha I minus 1, then minus di, okay, sin alpha I minus 1, okay. So this is second row. Third row, sin theta I, sin alpha I minus 1. I just did it, you also do it with your pen and paper. That will make you confident, okay, that how it is very simple. I minus 1, and if I make any mistake, if you work with me, you will correct me, okay. 1, huh? So by multiplying these two, you will get this. Hopefully I'm check. You can now you know. So these two matrix has to be multiplied, and this is very, very important. This is called mother matrix. So this is matrix we are looking for, okay, which is giving you the complete kinematic relation of ith coordinate frame with respect to I minus 1 coordinate frame. And this is very generalized approach. So you see, you can next I will show you that starting from here, any robot, say a designer has designed a robot and it is given to you as a planar designer. So first step will be to assign correctly coordinate frame, and then correctly figuring out the DH, 4 DH parameters, and then using this matrix I will be able to formulate all the matrices for the robot, okay, and that I will show you in my next class. Till then, stay tuned, and I hope this is very much so your assignment will be that you just change the order of this and this and this and this, but not this and this, okay. The reason is my ith coordinate frame is considered as a body coordinate frame, okay, and whatever operation you give should be post multiplied, and I minus 1, whatever operation you give in order has to be pre multiplied, okay. So that you also check, and you will end up with the same matrix if you are doing correctly. Thank you for your attention. Have a nice day. Stay safe. Bye bye.